Okay, in this video, I'm going to demonstrate how to calculate the velocity of a tidal current at any time. We'll be using this example problem on a scratch piece of paper and the tidal current tables from 1983, which are the testing tables for the U.S. Coast Guard. The tidal current tables are set up very similar to the tidal tables, and I have a video on calculating the height of tide at any time, which goes into detail about what the tables have in them. I'll go a little bit faster for this demonstration, so if you don't keep up, go back and look at the height of tide at any time video. Okay, so the tidal current tables, there are several tables in this publication. We are going to be using 4 sections of this publication. The first that we'll be using is Table 1. Table 1, again, looks like a calendar. It has reference stations, so large stations that we can base corrections on. Okay, it has the events every day of the year. So on March 1st, 1983, was a Tuesday, at 01:56, there was a slack water event, because this is a slack water time in hours and minutes. At 04:42, there was a maximum current event, okay? And the velocity of that event was 2.3 knots. And the event was an ebb because you see a capital E right here. So at 1:56, there was no horizontal movement of the water, okay, which is what a slack water is. At least no horizontal movement of the water due to from tidal current. And then the water started ebbing. Okay, so it was ebbing, and the maximum velocity of the ebb occurred at 04:42. The maximum velocity, which was at 04:42, was 2.3 knots, ebbing. After 4:42, it was still ebbing, right? It was ebbing all the way up until the next event, which occurs at 08:22, the next slack water time. At 8:22, the horizontal movement of the water due to tidal current was 0. So there was no horizontal movement of water. After 8:22, the flood started. So the velocity of the flood starts off slow and picks up and hits its maximum velocity at 10:33. At 10:33, the velocity of the flood, okay, the horizontal movement of water in the flood direction as determined by the port, is 1.6 knots. And we know this is a flood because there's an F, and also because it's following an ebb. Because you'll see it ebbs, then it floods, and it ebbs, and it floods, and there's always a slack water time in between. Okay, so that's what we have in Table 1. I'll also point out in Table 1 that because this is a horizontal movement instead of a vertical as it was in tides, we have a direction, right? And so tidal current problems usually ask for direction and velocity. Here in Table 1, we have a direction of the flood. It's generally 355 degrees true, and a direction of the ebb, which is generally 195 degrees true. That's only at this reference station. So any station that's subordinate to it, this would not be applicable because direction can change. If you can picture a river bending, 360 degrees is potential. So this is only directions for the flood and the ebb at this reference station, right? That's Table 1. Table 2, we have corrections, right? So here's an excerpt from Table 2. And we find here that at whatever number this is, index number, right? At Cape Charles, that in this position exactly, that one doesn't really apply. Let's see, Smith Island Shoal. Okay, it's Smith Island Shoal in that location. Okay, we have the following corrections. Okay, the corrections for the min before flood in time. Okay, the difference is from what the reference station of Chesapeake Bay entrance on page 64 is and what it actually is at the subordinate station of Smith Island Shoal. Okay, for the min before flood is a negative 2 hours and 14 minutes. Now, min before flood. I haven't talked about this yet. Okay, but the minimum before flood is the minimum velocity before the water starts flooding. So if you recall, I talked about a slack water event, okay, which occurs in between a flood or an ebb event. This, for all intensive purposes, for our calculations in this kind of example, is going to read a slack before the flood. Okay, so this is the slack water event that occurs before the flood. Possibly, it is not a true slack water. Some ports won't experience a slack water of 0 horizontal movement for long enough for it to be calculated as a true slack water. Sometimes there is always a horizontal movement. All right, and so that would be a minimum velocity. Maybe it goes only down to 0.1 and it doesn't ever go to a true slack water. But we can just, for our purposes today, call this the slack before the flood. All right, and then we have a time of a flood, and the time adjustment for this is subtracting 2 hours and 12 minutes from whatever the flood time is at the reference station of Chesapeake Bay entrance. Here, the minimum before the ebb, which would be the slack water that occurs before the ebb, has a correction. This correction is different than the correction made to the slack water before the flood. So we have to identify what slack water is. Is it before the flood or is it before the ebb? And then the ebb event has its own correction. To correct speed, we saw in table 1 we were given speed, maximum velocity, okay, of the event, the flood or the ebb. We use this speed ratio. We have a speed ratio for flood and a speed ratio for ebb. So in our example here of Smith Island Shoal, okay, the speed ratio, the correction that we're going to apply to the reference station is 0.3. How do I apply that? Well, it's a ratio, so I have to multiply. So whatever it is, the maximum flood at Chesapeake Bay on whatever day I want, I have to multiply it by 0.3 to get what it would be at Smith Island Shoal. Okay, and this happens to have the same correction for the ebb, but some stations have different corrections. We're always multiplying. It doesn't have an asterisk. We know to multiply because here it says it is a speed ratio. So for currents, it doesn't say plus or minus. We always know that we multiply, right? Here in this section of table 2, it discusses average speeds and directions. So here we have minimum before flood, which we can also call slack water before flood, right? Maximum flood, minimum before ebb, and maximum ebb. This is an average, okay? So the average at a certain point can be valuable, and I will show you why. The minimum before the flood average is 0. So usually the minimum is a true slack water, right? That's not always the case, but on this page it happens to be the case, right? The maximum flood is usually 0.3 knots, okay, on average. And its direction is 298 degrees. Now this we will be using. So if you determine that the water is flooding at whatever time you need to calculate, then you would use this direction for the direction of flood, okay? This port also has a true ebb, in most cases, average of 0. Okay, not always the case, but on this page it is. Okay, but here we get a higher value, right? Okay, usually it's 0.0 knots in the ebb, average, not usually. But the direction of the ebb is 0.68 degrees true. This is high value. If we determine, okay, that the water is ebbing at whatever time we're looking for, then its direction of flow will be 068 degrees true. So we will be looking up these two numbers, right, for direction. And that's half the problem. Okay. We're also going to be using table 3, the velocity of current at any time. This is two tables, table A and table B, and we'll have to choose which table applies to this problem, and we'll get there. And the fourth thing that we are going to use in this example is the index. Okay? So we're going to start in the index here in the back. And our example is asking for the direction and velocity, so two things, of the tidal current at Pine Creek Point on June 16th, we're always in 1983, at 12:45, zone description +4. I know this is a red flag because I know that the examples in this are generally Eastern Standard Time, okay, or zone description +5, so we're observing a different zone description than what this book is referencing. So that will come into play when we get into table 1. However, for now, we just start at the beginning. Pine Creek Point. Let's look it up. Okay, so here Pine Creek Point is has a table 2 number of 2816. Okay, just the same as in the tide tables. If it had an asterisk like this one up here, I'd know that it was a reference station. I could go directly to table 1 to get daily figures, page 28. Okay, but this does not have an asterisk at Pine Creek Point, so I'll have to go to table 2. Okay, 2816. So here I go. Okay. So 2816. Right here, Pine Creek Point, 2.3 miles south-southeast of, okay. And so sometimes it's handy to get a straight edge here and make sure we get all the figures correct. So that's what I'll do. All right, again, in table 2, we have time corrections for 4 different events. We have the slack before flood, the slack before ebb, the ebb. Even though we know it might not be a true slack, it's a minimum velocity event, and we're going to group the two together for this purpose only. And then we have speed ratios. We multiply against the maximum velocity. Okay, and then we're also going to be looking at the direction, the average direction of the flood and ebb, because they are looking for direction. So I'm going to draw a table here that looks very similar to this table 2. And then I'll be able to take the figures from here and enter them in. So looks very similar to the table I draw for my tide problems. I start off thinking about table 1, okay, my reference stations. And then table 2, which is my corrections to the substations. And then when I apply this correction, okay, to the reference station, I get the substation events. Okay, so in table 2, Pine Creek for this example is 2816. That comes in handy sometimes. And I know when I do get to table 1, I'll be going to the race, okay, on page 34, because this is my reference station. So I can put the race and 34. All right. Now I'm going to set up the top row, my reference. And so I'm going to put min before flood, okay, time. So this is time. And I'll put MBF, min before flood. And then I'll put flood. And then min before ebb. And then ebb. This is all time. Then here for my speed ratio, I'm talking about velocity or knots, nautical miles per hour. And I only have velocity calculated for the maximum. I don't calculate it for the slack water or minimum, right? So I have it for the flood and then also for the ebb. And then I also have direction. So here I can put direction and direction for the flood, okay, in table 2, and direction for the ebb in table 2 we can put here. This is in degrees true, right? So let me pull out my actual figures now that I have my table set up. I have to subtract 20 minutes on the min before flood, so minus 0, 0, 20. I have to add 6 minutes to the flood for the reference station, so plus 0, 0, 0, 6. Minimum before ebb, I add 21 minutes, plus 0, 0, 21. For the ebb, I add 23 minutes, plus 0, 0, 23. My speed ratio at Pine Creek Point is the same for both the flood and ebb. It will not always be the case, but here I multiply by 0.2 for both. And then the average direction of the flood is 272 degrees true, and the average direction for the ebb is 084 degrees true. All right. That's all the information I need from table 2, so I'm going to go to page 34 and look up the race. Page 34 will put us in table 1 at the reference stations. All right. Page 34 only covers January and February, so I keep going. There's March and April. And page 36, I find May and June, and I'm looking for June, right? I'm looking for June 16th. So here is June 16th. It happens to be a Thursday. I want to find the direction and velocity at Pine Creek, right, at 12:45 plus 4. So remember, table 1 is where I change the times to make them in my time here, which is daylight savings time, observing one zone to the east. How did I know that? This is in time meridian 75 degrees west. I divide that by 15 and I find myself in a zone description plus 5. If I'm in zone description plus 5 here and I'm observing plus 4 here, I need to advance these times by 1 hour to put them in plus 4, right? They're one zone closer to Greenwich. So anything I read out of here, when I write it down, I will add 1 hour. And then I will be done with daylight savings time. I won't even have to think about it. I will have applied everything on this piece of paper to match zone description plus 4, okay? So I don't do anything to this time. I only take these times and add 1 hour when I copy them down here. All right. So let me get back to it. 12:45 is what I'm looking for. I'm looking at June 16th. So I always start by looking for whatever event, either slack water or maximum current event, that looks like it will result in a time that's closest to my desired time. So here I have 12:50. I know that'll be 13:50 with daylight savings time, and it is a maximum current event. And when I scan across in the column, I see that it is a flood. For floods, all I have to do is add 6 minutes. So that time will be close to 12:45, okay? But, you know, more than an hour later. So let me go back in time and consider that the event that happened right before that is a slack water, okay, because it always happens where there's a slack at a flood, a slack and an ebb. So this is 10:02. It would be 11:02. And for my slack times before a flood, my min before flood, I have to subtract 20 minutes. So 11 minus 20 minutes, that'll also be close. These will probably be the times I end up with. So let me start off with I'll start off with my slack before the flood, okay? So my min before the flood or slack before the flood time is 10:02, so I'm going to write down 11:02. There's no velocity for this time because it's a slack water event, okay? So here I take 11:02 and I subtract 20 minutes. I work different with the minutes and the hours, right? So I'm going to borrow from the hours. I'm going to make this 10, and I'm going to add 60, so 62. 62 minus 20 will give me 42. So this is 1042 is my min before flood. That is before 1245. So now I need a time after 1245. So let's see if 1250 will cut it. This is, I have to spring this forward 1 hour, so this is actually 1350, and I know this is a flood event because I scan the column and see that there's an F here. So 1350 is my flood event, and the velocity of that event, which I put under the F, right, is 3.4 knots. So 1350 plus 6 gives me 1356. Is that before and after the desired time? Yes. That makes it so that I can use tabular interpolation in Table 3 to solve for this problem. If I found a time, if these times were not either before and after, one of each, I'd have to find a different event, okay? So because I can use these times, those are only times I will use. I'm not going to end up using any kind of ebb here. It just didn't work out that way, okay? So I'm working with the flood. I'm working with the min before flood, right? There was a slack water before the flood happened at 1042. And then it started flooding. And it picked up velocity in the flood all the way to 1356 when it reached max velocity. Okay, so the water is flooding at 1245. And because it's flooding, and I know the direction of flood at this substation is 272 degrees true, I've already got half of the question. The direction of tidal current at Pine Creek Point at 1245 is 272 degrees true. All right. So let's get back to it. Our interpolation, our velocity at the maximum event is something we're going to need when we get into Table 3. So I can calculate that right now. It's 3.4 knots times 0.2, which gets me 0.68, so 0.7 knots. So 0.7 knots is the maximum velocity for this event that occurs at 1356. So now let's go into Table 3 because we have all the information we need to enter. Okay, Table 3, we have Table A and Table B. Okay, and here it describes, this is how it describes how we use it, right? Or there's an explanation on the previous page. But here, use Table A for all places except those listed below for Table B. So probably we're going to be in Table A, but let's just check. Use Table B for Cape Cod Canal, okay, Hell Gate, Chesapeake, and Delaware Canal, and all stations where Table 2 is referred to, okay, where they refer to B in Table 2. So this doesn't apply to any of those. We're going to be in Table A. All right. What do we need to enter this table? We need interval between slack and desired time, and interval between slack and maximum current. What it will give us will be a ratio, which it'll say down here, okay, a ratio that we apply to the maximum velocity event to get the velocity at the desired time. So, interval between slack and desired time. This is different than what we did with tides, right? With tides, we thought, what happens closest to this event, this time? With currents, this says interval between slack and desired time. So we're never comparing this desired time to the time of the maximum velocity event. We're always comparing it to this minimum event, this slack water event. Okay? So, interval between slack and desired time is 12:45 and 10:42. right? So we have 3 minutes here and 2 hours. So 2 hours and 3 minutes is the interval between slack and desired time. All right, so then from there we go interval between slack and max. Well, here's the slack, 1042, and here's the max, 1356. So the difference between those two times, 1356 minus 1042. Okay, 56 minus 42 is 14, so 14 minutes. And 13 minus 10 is 3, so 3 hours and 14 minutes is the interval between slack and max. All I need to enter this table is 2 things, so I'm ready to go. Interval between slack and desired time of 2 hours and 3 minutes. I find whatever is closest, right? So 2 is closest. I have 140, I have 2, and I have 220, so I'm going to 2 hours. And then the interval between slack and max is 3 hours, 14 minutes. So I have 3 here and I have 320 here. I'm closest to 320. I scroll down and find 0.8 is my ratio, okay? So I'm going to call it my my correction ratio here. And I apply it to the maximum velocity, right? So if my maximum velocity is 0.7 and my correction is 0.8, right? I find a velocity of 0.56 or 0.6 knots. Okay, 0.6 knots at 12:45, zone description plus 4 at Pine Creek Point. Okay, that's half of the problem. In a direction of 272 degrees true. So this is the other half. You need both this and this, right, to get the problem correct. So that's my answer.